say, just so we're all on the same page. So in sort of the classical case, the setup is that I have some variety, say x, in Pn, and let's say its dimension is P. So then I can ask about the degree of x. There's a few ways that you might like to think about this. Sort of geometrically, this is like the intersection, the number of points of intersection of x with just some general linear space of complementary dimension. And so these will intersect in general in a finite number of points. I count them. This is the degree of my variety. Algebraically, you might be happier thinking about the degree of x is also p factorial times the leading coefficient of the Hilbert polynomial. No, it wants to go on the top. Yeah, yeah. Polynomial. Okay, great. So yeah, so if you're more geometric, maybe this is how you like to visualize this. If you're algebraic or really like Hilbert series and Hilbert functions, maybe this is your preferred way. But regardless, these are going to be equal to each other. And if x, so the variety that I'm looking at, if it is non-degenerate, which is going to mean that it doesn't lie in a linear subspace. Okay, so it doesn't secretly live in some smaller space. If this is true, then the degree of x has a lower bound, and it's given by its codimension plus 1. Okay. All right, so this says that like in P2, a line is contained in a line. Right, this is the startling mathematical fact of the day, right? Okay, so these are this is the minimal degree that a variety can have. Anything with lower degree than this will be degenerate. And there's a theorem, which is in part due to Del Pezzo in, I can't use an apostrophe for this one because it's 1886, and Bertini in 1907, according to my notes. And the theorem is a complete classification of all of the varieties that actually have this minimal degree. So it says that if x is non-degenerate and not a hypersurface, if it's a hypersurface, it's a quadric. It's like cut out by a quadric, right? So, okay. So, but if it's not a hypersurface, then there's only a few things it can be. So it can be a rational normal scroll. Yes, yeah. Non-degenerate, totally. And minimal degree. No, the crazy fact of the day is that every variety is a rational normal scroll. Wouldn't this be a great place to live? Yeah. And minimal degree. Then x is a rational normal scroll. Or the Veronese surface. P2 in P5, or it's a cone over one of those things. So if it's smooth, it has to be a rational normal scroll or P2 embedded in P5 by the Varieties. If it's singular, then it might be a cone over, it will be a cone over one of those things. Okay, and these are all of them. There's no other varieties that are non-degenerate and hit this minimal degree bound. Okay, is this part of the picture feeling clear? Okay. Okay, and so one of the, there's some nice things about these particular varieties that achieve this minimal degree bound, and they have some nice connections to study of syzygies, of projective varieties. So there's, let's see. So if I have a minimal degree variety, they have relatively simple syzygies. These are just some nice facts. So in particular, all of these varieties that have minimal degree, they're cut up by quadrics. They also have linear resolutions. So if I look at the minimal free resolution, all of the maps are linear. And if I want to like think of the Betti table looks like these are all zeros. So my only non-zero entries are like in this second row, depending on if I've decided to resolve the ideal or the quotient ring. So I'll have everything living in this second row. And so if you're more familiar with syzygies, we would say that these satisfy the NK condition for all K, which literally, almost literally means what I've told you, plus another like a projective normality condition. Okay. So these have nice syzygies, and also there's also like some other connections. So there's also like Green's KP1 theorem, which says that it identifies things that are a subvariety of a minimal degree by certain Kazul cohomology non-vanishing. There's other connections to syzygies. There's like the Gruson-Lazarusfeld-Peskin theorem, which relates the degree and the regularity of a curve. So let's write Green's KP1 theorem. Okay. So these have some nice connections to syzygies. And they're nice, they sort of like they totally characterize these things that are sort of entirely contained in the second row. So actually anything that looks like this has to be a minimal degree variety. And so if you're either just interested in studying degrees of varieties in weighted projective spaces, or if you're interested in studying syzygies in settings that aren't just weighted projective space, it might be nice to try and develop a theory of minimal degree varieties as a place to kind of look for varieties with simple syzygies and explore some of these connections between like different notions of degree and regularity and simplicity of syzygies and things like this. So our main question / goal, I guess, is we want to know if we can formulate a meaningful theory of minimal degree varieties in weighted projective spaces. Okay. And this is sort of a kind of specific goal. You could also ask this like in other toric varieties, or if you're interested in like embedding things into other toric varieties other than PN. Yes. Yeah. I think that it's minimal degree if and only if it's NK for all. Okay.
I guess it depends if you're considering non
Sure, I would want it to be irreducible. Yeah. Yeah. Good point. Totally.
Okay.
Yeah. Now is maybe when I get to be one of those annoying people who's like, oh, variety has to be irreducible because that's the definition I've chosen. But yeah. So that's a great clarification, totally. Okay. Okay, so yeah, so this is going to be kind of the main goal, and then maybe to expound on like what it would mean to formulate a meaningful theory of something. Really, the kind of things we want to know is there some lower degree bound like this for a lower bound like this for the degree of a weighted projective variety. We might want to know if we can classify them all in kind of a la Del Pezzo-Bertini theorem here. And might also be interested in connections to syzygies and see if we can say things about like them having nice syzygies, things like that. Okay, so these are going to be the goals. Questions, additional comments, or corrections so far? Okay. Okay, so now in order to do this, we're going to have to kind of come back here and figure out there's various things that need to be figured out on kind of this board in order to make sense of this. So some key definitions that we had here that we're going to need to reformulate are we wanted to only think about non-degenerate varieties. Otherwise, it's a silly question because we can have like lines. And we also want to know like what the degree of a variety should mean. And these are both maybe challenging things to think about in weighted projective space. This one is maybe easier to see that it's hard to think about in weighted projective space because lines are a little confusing. So we're going to need a good analog for like how we should be thinking about the degree in the weighted setting. Let's start with that. So our setup now is we're going to take some integers, some positive integers. And I'm going to define first what is the weighted projective space with these weights. So let's look at polynomial ring in as many variables. I think I said n. And I'm going to grade it by saying that the degree of xi is equal to ai. So I'm still z-graded, but I'm not standard z-graded anymore. And so then what I'm going to do is I'm going to take my weighted projective space with these weights to be proj of this polynomial ring, graded proj, weighted proj. You can also write this as, this is also going to be a n plus 1 minus the origin. And then I'm going to mod out by my scaling relation, just like in like a straight projective space. But now the scaling relation is that I have something like T0, Tn should be equivalent to lambda to the A0, T0, lambda to the An, Tn. So my scaling relation is weighted by these weights. Okay. So this is going to be my setup. This is how we'll define our weighted projective space for today. And so now if I have some variety in my P A0, AN. Now it corresponds to some homogeneous, weighted homogeneous ideal in S. And we'll say that X is non-degenerate if this IX is contained in the square of the homogeneous maximal ideal. So kind of thinking about this, what do we want to avoid? We want to avoid an equation that's just like xn minus some polynomial in the other x's, because then I could replace all my xn's and I could be thinking of this in a smaller weighted space. Okay, so we want to avoid that. So we'll say this will be our definition for non-degenerate. It's the same algebraically as in the standard case. Okay. So now my ideal it has a Hilbert function still. Still an integrated polynomial ring. And the Hilbert function is no longer eventually going to be polynomial, but it will eventually be quasi-polynomial. So, which is eventually quasi-polynomial. And great question is, what's a quasi-polynomial? And so this is going to be something like, you know, I think an example is better than the actual definition. This is going to be something like, you know, t squared plus 3/2 t minus 1 when t is 0 mod something. T squared plus t minus 3 when t is 1 mod something, etc. So it's sort of like periodically polynomial. Yeah. So in general, exactly. In general, we can write a quasi-polynomial who's with period equal to the LCM. Sometimes you can get away with smaller, so sometimes you'll have something lower. But the LCM of the weights will be enough. Okay, and this is a totally invented one. I don't know if this belongs to anyone, but sort of what I wrote down here happened to have the same leading coefficient. This also won't always happen in general. You can, and it might not be super hard to convince yourself of this actually, because it's not hard to cook up one that's like only non-zero in even degrees or something, right? So like definitely this is not always going to be the same. There are circumstances where it will be. So in particular, all of the examples that we'll do today, all of the weighted projective spaces today will have the property that their subvarieties will have a constant leading coefficient. But what we can do is we can always take sort of the piece of the polynomial that's 0 mod the LCM of the weights and call this the leading coefficient of the quasi-polynomial. Yeah, so this is a good question. And it has to do with something with a map that we can write down to re-embed our weighted projective space into just a straight projective space, because all of these weighted projective spaces are projective varieties. And so we want like whatever things we define for the weighted projective space to play nicely if we happen to re-embed the entire picture back into a projective space, and this is going to be the one that is the correct choice for that. Okay, so it's going to have a Hilbert function is eventually quasi-polynomial, and is there a, oh no, sorry, I thought there was a, and we're going to take its leading coefficient. It's like leading coefficient. And we're going to define the degree of x using that leading coefficient, just like we did in this case. So it's eventually a quasi-polynomial. And so we're going to, yeah. Yeah.
Is that equivalent to something like a name? Or...
It might be.
Is there something combinatorial about the degrees, for instance?
So yeah, so the reason it'll be okay here is going to be because we're always going to have a weight of 1 and we're always going to have a prime ideal. And these two things happen to imply this. There's something called, I think they call it like the grade of the quasi-polynomial or something. And I'm forgetting the paper, but yeah, there's something that someone has defined as like the grade of the quasi-polynomial that measures the highest power where the coefficient is constant.
A condition that I've seen, not for
Mhm.
necessarily apparent in like sort of thing, is that the degrees, each pair of them, or no, each subset other than one has a GCD.
It's something like this, but so I think it might not be exactly that, but that's probably enough to guarantee it. If I don't want to, I'm not going to stake a hard claim on that, but that sounds like it's probably enough to guarantee it.
Maya, sorry, can you repeat the question?
Yeah, oh, totally. So the question was like, what is a criterion? Is there a combinatorial criterion or something for all of the leading coefficients on the Hilbert quasi-polynomial to be constant, to be the same? And the answer was, I don't know. Probably something, it's something about the GCDs of various subsets of them.
All right, thanks.
Yeah, no problem. Okay. So let me write down this important definition and then we can get back at it. So, okay, so we're going to say that the degree of X is going to be, again, say dimension of X factorial times leading coefficient of the Hilbert quasi-polynomial. Okay. Other questions about our setup? Yeah.
Is this equivalent to doing it sort of an intersection theory kind of computation
So,
in this case?
so I want to say yes and no. There's a big problem, which is that these are not smooth. And so if you have an intersection in like the singular locus, then you have to deal with that. It should be the same. So I'll write down something in a second that will relate it to sort of the intersection theory, I think. Which is, yeah, I think sort of like underlying this maybe is that it would be nice if the degree was also counting some type of intersection numbers. So yeah, let's see it. Yes, yeah.
So
Yeah, so you can do, yeah, it does work. Yeah. Yeah, so I think the answer is that like, yes, it has to do with some, there's some intersections. We have to be careful because we can't like intersect with lines in the same, like with like planes in the same way. But yeah, so let's maybe make a note about this, which is that if Q is the LCM of my weights, then there's for some K, O of K times Q is very ample on my weighted projective space. And this gives us this map, an embedding from P or weighted Pn into some bigger Pn. I'll call this U. And so what we want is and this also gets back to Patricia's question earlier, is that because we'll always be able to do this re-embedding, we want to make sure that degree, the like notion of degree makes sense sort of under this embedding. And so when we do this, so let's say X is in here, and let's say its image is Y in here. So the Hilbert functions are related. Well, the Hilbert function of Y, HF stands for Hilbert function. Now we all know. If I plug in some integer, this is like plugging in k times q times d into the Hilbert function for x, because that's the degree of the map. And so this tells us that the degree of the image of x is k q to the dimension of x times the degree of x. And so now, sort of from an intersection theory standpoint, this is saying that if I want to take some like general high degree hypersurfaces in my weighted space, look at their images, which are now going to be linear under this map in here, look at the intersections, and then I want to come back and like scale by something. So it's going to have to do with the intersections of sort of the kind of the fairest choice of linear thing you could take in the weighted space. But this might have to have like higher degree than 1, for instance. Okay, and in particular, for this to be true, and this is like how we would want this to behave for like degree under a map anyway. And so this is why this will be true if we pick that leading coefficient, but it won't necessarily be true if we pick one of the other ones. Okay. Questions?
So this isn't saying that it's okay.
Yeah.
It's fine.
Yes. Yeah. That's right. Okay. Yeah. Yeah, I mean, so the map on the polynomial rings is you take all of the monomials of degree kq. Yeah. Okay. So, okay, so I want to narrow down a little bit, because one thing that people might know who have worked with either like weird like polytope stuff or weighted projective spaces in particular is that these are like really grotesque to work with. They're really challenging, and kind of like Maher alluded to a little bit, there's like all this nasty stuff with GCDs of subsets of things, and it becomes very challenging to work with. So we're gonna narrow down, we're gonna restrict. From now on, we're gonna look at just some of these. So we're gonna restrict to weighted projective spaces where there's a bunch of ones, and I'll denote it like this. I have A ones in the weights, and I have B of some other thing. Okay, so I've narrowed down a lot. One reason to narrow down all the way to these, so one, they're more tractable. Two, these are some weighted projective spaces where there is some work on some of these like syzygy questions, and so it's a nice place if we want to kind of compare minimal degree results with results on syzygies. This is a nice place to work because some of that work has already been done. Okay, and these also have this property that I can just take O of the LCM itself. I don't have to multiply by anything, and the LCM is M. So here I can take this map. So if I look at the map given by OM, this defines a closed embedding. Into MPN. And it's got, this map has a nice property, which is that minimal degree varieties, so if I have my P1 to the A, M to the B, PN, I'm going to call it new again. Something that's minimal degree over here is going to go under this map to something that's minimal degree in its linear span. So I mean, it's gonna go to something, right, I haven't told you what the minimal degree over here is. But I will. So there is a minimal degree thing. Once I tell you what it is, it will be the case that things that achieve this minimal degree here, they're gonna land probably on something degenerate over here, but they're gonna land on something that's minimal degree in its linear span. Okay, cool. So, okay, so great. So now let me tell you what the minimal degree is. So, here's a proposition. And so the proposition says, if I have X and it's going to be irreducible, non-degenerate, p-dimensional variety in p1 to the a, m to the b, then its degree has to be at least, and there's a couple of cases. So a minus 1 m plus b plus 1 plus b, whatever this fraction is. This is going to give us our minimal degree. It looks very opaque at the moment. When the dimension is relatively small, and the dimension gets big relative to sort of the non-1, how much of this is weighted in something other than 1. Dimension gets big, our minimal degree bound changes. So there is sort of a notion of minimal degree, and it will satisfy this property here. Okay, so we have, this is like a first step of like, we want to study things in minimal degree, we should know what degree we're looking for. And so now we want to know, who are they? What are varieties?
Are the degrees of X always integers?
Absolutely not. Yeah, and so they'll be like, they're really not going to be integers most of the time. And from like an intersection theory standpoint, like this is something that happens when you have singularities and you intersect in like the singular points, even in like a standard case. And so because this guy has a relatively big singular locus, we wouldn't expect these degrees to be integers anyway, often. That's a good question that someone who does more intersection theory than I do can probably answer better. Does anyone? The question was like, geometrically, how do you make sense of a fractional degree? Yeah, and I feel like I have to punt on this one because I don't do a lot of like actual intersection theory. Yeah, this is a good question though.
It's like any path.
Yeah.
You know, intersection. One of them. Then that's
Okay. Okay. Yeah. So these will often be fractions and they'll look weird, but they do have like a well-defined minimal degree that they can have. And we can write down varieties that do hit this minimal degree, so we know it's sharp. And so we want to know what they are. So
Can I ask a quick question before you move on?
yeah.
Even in this case of having A1s and BMs, can you describe the singular locus? Is there a way
Yeah,
of?
so the singular locus is where all of these variables are 0.
Okay, so those are the only singular points.
Yeah.
Okay.
this bound have any interpretation like the previous one connection for invention?
Yeah, so yes. It kind of, in that, like, if you kind of look through this and piece it out a little bit more, like the difference between like the a, like the right, like the dimension, the codimension is a plus b minus 1 minus p, and so there's some scaling that's happening for the for the non-1, for the non-m weights, that's kind of obscuring it. Yeah, so in particular, I guess maybe something to point out is that, like, it's not like just the codimension, it's like also sort of, yeah, like how much of that codimension is coming from A's versus B's in kind of a vague sense. Okay. Wait, that's the one I just went up. Not that it really matters. Okay. Okay, so I want to tell you what the varieties of minimal degree can be and some things that I know about them. So, let's start with curves. So the first thing to tell you will be what irreducible non-degenerate curves of minimal degree are. So if this is theorem okay, so let's let C be an irreducible non-degenerate curve in P1 to the A and to the B with minimal degree. And so now notice that I'm always, if I've actually chosen a weighted projective space and not like just let B equal to 0, I'm always going to be in this top case because P is 1. Okay. And now you got to switch it back. Okay, so if I have one of these minimal degree, then so 1 so this is still a rational curve, just like in the standard case. These are rational curves, and up to a change of coordinates on my P1 to the A, M to the B, C is determinantal, and it's given by the minors of a nice matrix. So C is put out by the 2x2 minors of a matrix will look like this one. So it's like I want to write down a rational normal curve because that's what I feel in my heart should be minimal degree. But unfortunately, right, I'll get to this step. So I'm going to have my x's are going to be my variable, my degree 1 variables. I'm going to use y for the degree m variables. So I want to say it's this, but there's a big problem, which is that this column will give me lots of minors that are not homogeneous. So then I think to myself, what's the absolute dumbest way I could possibly fix this? And that's what we do. Okay. So all of these curves of minimal degree are going to be cut out by matrices that look like this, up to a change of coordinates. And we want to think, you want to think about these as analogs, weighted analogs of rational normal curves. And if you want to know more about these, you should look up a recent paper from Caitlin Davis and Ola Sobieska for more on these curves. Okay, but for purposes of today, what's important about these is that they're minimal degree, and all curves of minimal degree will look like this. Okay. Great. Questions, comments, concerns? Excellent. Okay, so now we have our minimal degree curves, and I want to try and use this to think about minimal degree varieties in higher dimensions. So let's recall, oh my God, all right. I assume that in the past, everyone who's made that sound was being a diva, but I'm sorry, everyone. I shouldn't have assumed. Or maybe you were, and I am simply also a diva. Okay. So now we want to know, what about higher dimension? So let's maybe remember or see for the first time that so back in like the classical case, most of our varieties of minimal degree in Pn are weighted, or are not weighted, are rational normal scrolls. So we're going to set aside the Veronese surface for now, because most of these things are scrolls. And how do we, what is a scroll? Well, we want to take like a bunch of these rational curves. So, or like in general, so if I have a scroll, what I do is I have like my curves. Here's two of these curves, and then they're both like parametrized by P1. So I get a line, I get like a family of lines parametrized by P1. So I get like this variety, right? So this is a scroll. And so in kind of the classical case, our scrolls, they're built up by our minimal degree curves. We pick minimal degree curves for all these curves, and then we build this scroll from them. And these are our minimal degree varieties, other than the Veronese. Okay, and so what we want to do is we want to see, well, like what should our weighted scrolls be? Can we do a weighted scroll that is minimal degree? So we want to know, what is a weighted scroll? Okay, and if I look back at this picture from before, if I want to describe it, if I want to describe like the equations, what I do for this is I say, well, each of these curves that are in my scroll are cut out by 2 by 2 minors of a matrix. So I have like a block here that I'll call S1, cursive S1. And then I'm just going to concatenate the two blocks. And this is the matrix that cuts out this variety. So I want to do the same thing. Let's see if we can just do the same thing. So what we're going to do is we're going to say that our weighted scrolls are going to be varieties that up to a change of coordinates, we want this to be, let's see. I'm going to say up to change of coordinates, a weighted scroll is up to change of coordinates. I'm not gonna write that. We want it to be cut out by the minors of a block matrix. And our blocks, well, okay, so each block, in each block, I'm only gonna use like a subset of my variables. So I have to tell you how many x's I should use and how many y's I should use. So I'm gonna denote that S A1, B1, right? So I'm gonna have all of these blocks that look like this. A, P1, P, P1. And then it turns out that we actually need to be a little more careful. We can't just call it quits here. Because we want to make sure that we're accounting for blocks where I actually have not used any of one of the weights of variables. So I could write down a block and like, we don't see these at the level of curves because they're not going to be curves because they don't cut down the dimension enough because they don't use enough variables. So I need to make sure that I'm allowing blocks that are all A's. And so I'm going to do that by just saying that this second parameter is 0. But it's going to be useful to count the blocks that are all Y's separately. So if I have no X's, I want to do a different type of block. And I will use cursive T for these. B1 plus 1. Okay. And I'm going to count the number of each block that I have. So it's a B. I start counting. So I called this last one P1. I started counting at P1 and I went up to P. And P is going to end up being the dimension. But so I have P1 of these guys, and I have P minus P1, which I'll call P2 of these guys. So this is going to be, we're going to say this is type P1 comma P2. And note its dimension is P, the total number of blocks. And I'm going to assume, actually, this is very important. I'm going to assume that I've used up all the variables. Okay. So I guess what this means is I want to assume that if I sum up all the AIs, I get A, and that if I sum up all of the BIs, I get B. Okay. Otherwise, I'm just looking at a cone over a smaller one. Okay. Great. And so now, like two more things to tell you, which are, that was a silly order of operations. Okay. And so now we've defined these weighted rational scrolls, and the hope is that these will be some of our varieties of minimal degree in weighted projective space, if we think that things should kind of shadow the case for our straight projective space. And where things will now start to change a little bit is that this is only sometimes going to be true. So is our theorem? Oh, whatever. You know our names. Is that, so let's say very curly S is going to be scroll. It looks like a scroll. So this is going to be a scroll of type P1, P2. So then S has minimal degree. If and only if P1 is 1. So I have to have all one, I have to, up to change of coordinates, be able to put all of my x's into one block in order to have minimal degree. Okay, and now there's a couple things to note. So, yeah, so there's a couple things to note. One of which is, I'll just say it, is that there's some limits on when this can happen because each of these blocks has to have at least 2 y variables, right? It has to have a column. And so if I run out of y variables, I can't have that many of these blocks. And so what that says is that actually there are some cases where there are no minimal degree scrolls. There are some choices of A and B in dimension where there's no minimal degree scrolls. And yeah, and that's just the way it is. But furthermore, this will also, so I will get started like a couple minutes late, which means I should finish now. Okay, so sometimes there are no minimal degree scrolls. And so you might wonder, are there other things that are minimal degree instead? So here is a partial answer to this, which says every smooth variety of codimension at least 2, so we're going to exclude hypersurfaces again, in P1 to the A and to the B is either, okay, there are few options. So this could be a surface in P1, 1, 2, 2, 2. It could be a surface in P1 m to the 5. Or it could be a weighted rational scroll. Okay. And so what this also says is that there are some weighted projective spaces, some of these P1 to the A, M to the Bs, where if you look for a certain dimension, there are just no smooth varieties of minimal degree in that dimension. Okay. So I think I will not write anymore. I will say 2 things to connect back to some of the stuff that the motivation I mentioned with syzygies, which are that so in the classical case, we had our minimal degree varieties had this N1 or this NK condition for all K. And something that is still true actually in the weighted space is that regardless of whether or not the scrolls have minimal degree, these weighted scrolls will satisfy sort of a weighted version of this NK condition for all K. So this is no longer something that's characterizing minimal degree things. But we can still see differences in regularity between the minimal and the non-minimal ones for a couple different notions of regularity that we might define in weighted space. Yeah.
You said the non-minimal
Yes,
ones
even the have the weighted NK condition for all K. So if it's a scroll, even if it's not of minimal degree, it is still like maximally weighted NK. But if you want to instead if you want some sort of syzygetic way to see these as different, you can look at their regularity. And there are a couple different notions of regularity that you can look at that will distinguish between minimal degree and not. Okay. That is all that I will say about that. Yeah.
So we guys thought about like, you thought about what would happen then in a multi-graded case? Is that the next stage?
That is a next separate project. Yeah. So this is also a great question. So yeah. So this is a further question, and I would say that so this is something that Greg Smith and I have been working on. And I will say that there is as many and more weird multi-graded and non-standard graded things to figure out before you can even sort of formulate what this should be. Yeah.
Does this weighted MK from A imply anything like it's not going to try to be linear resolution, but maybe resolution of variables?
Yeah. So great question. So what this means is basically, so what you want to do is you want to say, well, what should linear mean for a weighted project for a non-standard graded ring? And if I look here, I'm like, well, like I have got things that are degree 1, so maybe linear should mean degree 1. But somehow this isn't fair to the degree m variables because they never get to be linear. And so in fact, what we want to do is we want to say that any variable on its own should count as linear. But then we kind of have to allow things like x1 to the m is also linear. So basically anything that has the degree of a variable should be considered linear in some sense. And then, you can kind of look, then you can say, well, what does it mean to have a linear resolution? You want to look at how, at the entries in the matrix from that perspective.
Sorry, I have an elementary question. So I know what's a linear change of coordinates in the usual projective space is
Yeah,
clear.
totally.
What do you mean by up to a change of coordinates here?
Yeah, so this is a great question. So if you want to do like an automorphism of P of a weighted projective space, you basically have to allow a change of coordinates that like sends y to a degree m polynomial in the x's as well.
So long as it's just degree preserving, that's enough. Is that what you're saying?
Yeah.
Okay.
I think my question is kind of related to that. The regular projective space, for example, the Veronese E25 it's stable under the action of general metric.
Yes.
And I think the rational norm was supposed to.
Yeah.
So wondering if there's some kind of could be the GL of the variables in here, but then it's so maybe you should just have the automorphism group of that.
Yeah.
Projective space still. Quite a notch.
This is a good question. And I'm not confident in the answer, so I'm not gonna go for it. So I guess maybe the question is like how many classes of these are there that are like, are they all the same up to, if you fix sort of the type, are they all the same up to automorphism or not?
Sense of bearing.
Mhm. Yeah, totally. Yeah, so this is a good question that should be thought more about by me and others, probably.
Different setting, but maybe there's something very different. I think it's known when these weighted projective space are when the project polynomial, right? I think no, it has to do. I thought it had something to do with A0 to AN degrees, like GCD.
Right. So basically, so you can do this reduction of weights things to get to one of these projects. You want for no n-1 of the weights to be the same, or or to have the same GCD. Yeah.
Particular rings of invariance.
Mhm.
About
Yeah.
Who's fun.
Yes. Yeah.
So, is there any what? Studies which in some way might be.
Yeah, I think this is a great question. And I don't know. I think so. Yeah. So I think it's a great question, and like certainly one of my follow-up questions from all of this is that like I would like to be able to understand like other weighted, like this is a very restrictive class of weighted projective spaces, and it'd be nice to be able to understand others. So yeah, and I think that looking in places where maybe you have this invariant this structure might be helpful because there's some extra structure that controls some of the behavior, so.
Okay, there are no other questions. Let's thank Maya again.